Let's begin. We'll catch up with confidence intervals. We were working with trying to estimate a population mean from a sample mean, okay? And we call the point estimator, the sample mean itself is a single point estimator for the population mean, but obviously it's not accurate because if you draw another sample, you're gonna get a different point estimator. Draw another sample, you're gonna get a different point estimator. And then we argued it's better to put bounds on that point estimator, plus or minus, within a certain confidence level. And we call that the confidence interval. And a 90% confidence interval means that if you were to take 100 samples, 90 of them are gonna have the true population mean in the interval. Now, each sample is gonna have a different interval, agreed? Because the sample point estimator is going to be different, and then plus and minus that error margin is going to change depending on the sample you take and its standard deviation. And we had two things we had talked about. Sampling distributions of, if we know the population standard deviation, then we use what's called a z-test, but that's rarely the case. In the case where we do not know the population standard deviation, which we don't in practice, so we have to substitute that with the sample standard deviation called S, and in this case, the sampling distribution of sample means follows a t-distribution, which captures a little bit of the error of lack of knowledge of the true population standard deviation. It does a better job, it's more accurate. You can still use a z-test and assume that sigma is the sample standard deviation, so you can put S up in the first formula. And, you know, you're going to commit a little bit of an error. This is going to give you a better estimate when you use the t-test. Okay, so this is called the t-test t-distribution. So remember that we capture x bar is the sample point estimator, the sample mean. T alpha over 2 are these points in the tails, the critical z values. Area to the left or area to the right is alpha over 2, and alpha is 1 minus your confidence level. So confidence 90%, alpha is 10%, and n is the sample size, and s is the sample standard deviation. And we talked about how we could do this with Python. We're going to Pythonify everything, and eventually we will write a script to do confidence intervals for us, but you need to understand the mechanics. You know, I was thinking over the week, I work a lot with artificial intelligence. I work a lot with AI, okay? But you should see my conversations with AI, how they quickly turn into, you moron, this is not the right answer. What are you giving me? What BS are you giving me? You should see all my conversations. I give up, and then it gets angry at me, and the next chat, it's mean to me. I'm like, good grief. And so I have to switch to go to Gemini or go to Claude and start kind of playing the AI game. But it's just like it just invents stuff trying to please you. I don't want you to please me. Just tell me the truth, right? Just stop giving me nonsense. But I realized that I realized that especially for you, for your generation and the generations that are coming after you, like my kids, they're going to be placed in a world where there's this amazing tool that gives you the illusion that it knows everything, right? And it does so much. I wrote a code that would have taken me 6 months. I wrote it in 2 days last week. But for goodness sake, I knew exactly what I wanted to do, and I knew when it was giving me nonsense. But do you know if it's giving you nonsense or not? Now, how do I know? It's because I did it the hard way before using the AI tool. So I've done it. It's like I almost used an abacus to do a calculation before using a calculator, right? And that's what I fear our curriculum is going to possibly fail you. And my argument with teaching committees and curriculum development in the college, I'm like, how do we integrate AI tools and make the students, like, augment the students? I'm like, This is these tools are the more reason that you need to know the fundamentals, because you are going to be a prompt engineer and you're going to be a BS detector from all of the AI tools that are going to come your way. If you can't tell that it's giving you something that's nonsense, that's not grounded in theory, because it found 2 papers out there and interpolated the result to try to give you an answer that is satisfactory to you, but only you can tell that that answer is nonsense. Possibly another AI can tell, but you cannot play that game. So there's more reason for you to know the fundamentals, what's going on behind the scenes. So yeah, we use Python. We're going to use the confidence interval script, but you need to know how to use it. You need to understand what's going on behind it. And so there's more reason to understand the fundamentals, and it's harder on you. It's harder on the generation after you that's coming after you, because there's this tool that makes everything easy. And why not? Why not do that? So keep that in mind. Keep that in mind. I know it's hard. It's very tempting to just go on the AI. And I have some of my PhD students use it a lot, but we spend an entire hour talking about one plot because they don't understand what the AI gave them in that plot. Turns out it's wrong because they didn't know what they were doing. So be careful of that delusion. It's going to get better. It's going to get better at making things up, but it's the more reason for you to know the fundamentals. So I'm confident. My confidence interval level is 100% that you need to know the fundamentals. So, okay, coming back here, we have tools in Python that allow us to compute the confidence interval. The same way we did with the Z statistic, stats.norm.interval. We can use stats.t.interval, and we did an example on that in Python before we left. And the example was this one. Dental researchers want to estimate the mean leakage measured in nanometers of a new filling material for cavities using a simple random sample of 10 trials. As the population distribution is normal and the population standard deviation is unknown, so that tells us it's going to be a t-test. Find the margin of error for a 95% confidence interval for the population mean, given that the sample standard deviation is 15.5. So if you pull up your Jupyter notebook from last time, it was confidence, 2026 confidence intervals. I think that's kind of what it's called on my end. Confidence level, and for those on the back. So just have that handy, and we put in the numbers. 95% confidence, sample size is 10, sample standard deviation is 15.5, alpha is 1 minus the confidence level, and then we do the reverse lookup for the t distribution. So we want to get the critical t value, t alpha over 2, such that the area to the left is alpha over 2. So once you get one of these t values, you can get the other one. And then you get the t minus and the t plus on the other side because they're symmetric. So this one gives you the t value to the left. It's going to be negative. And the t value to the right is going to be the mirror image. So you take the negative sign of that. So that gives you the t values. And then you can compute the error margin, which is t alpha over 2 times standard deviation over square root of n. Okay, so we do that. Now you can't use the stats.t.int. Can you use the stats.t.interval on this? So let's ask this question. It's particularly for this problem. So this problem does not give you the sample mean. Okay? Does not give you the sample mean. But stats.t.interval gives you the full confidence interval, not the error margins, gives you x bar plus error and x bar minus error. Okay? So the standard way of using the stats.t interval is to give it the sample mean. But we don't have a sample mean. Can we use it to get the error margin? So stats.t.interval gives you sample mean, gives you this value that you put in, plus minus the error margin. What could you use this to just get the error margin? Yes? So it's not going to work, but you have an idea? It's still going to be, I mean, you take the difference and then the midpoint. What if we put a mean value of 0? The error margin, the error margin, is it dependent on the mean value? It's not. It's T alpha over 2 times S over square root of n. Has nothing to do with the mean value. So if you put a mean value of 0, what you'll end up mu equal minus E, between minus E and plus E. So let's test that. I'm going to come here. So that's a little trick we're going to use later to be able to, to just overcome all of these steps here. So what I will do stats dot T dot interval, and of course it's not very helpful, the documentation from SciPy, so I'll use the one in the slides. In my slides, the way we use this is we give it confidence level, degrees of freedom, location, and scale. So here's what I'm going to do. I'm going to give it df confidence C, and then df is equal to n minus 1. And then what was the other one? Location. I'm going to give loc equals 0. And then scale equal, the scale is going to be S over MP dot square root of n, right? Okay? And then when I do this, look at that. It gives me minus 11.08 and 11.08, which is my error margin, right? So this loc value only shifts that interval. So if I put 1, it's going to be minus 10 to 12, right? Minus 10 to 12. If I put 2, it's going to just simply add that value to the error margin. So that's how you can trick stats.t interval to obtain the error margin only. So you don't have to go and call the PPF and then compute the error margin manually by hand. Okay? Just a little trick. Internally, Python is doing all of that. So around 0? It is symmetrical around, it's symmetrical around the mean, right? Yeah, so if you put 0, it is perfectly symmetrical there, right? Okay, so that's kind of the example. Another example, in 6 determinations of the melting point of an aluminum alloy, a chemist obtained a mean value. Okay, so now we have the mean of 532.26 degrees Celsius. With a standard deviation of 1.14 degrees. If he uses this mean to estimate the actual melting point of the alloy, what can the chemist assert with 98% confidence about the maximum error? So first you turn this problem into a math problem, or you just kind of put in the values you care about here. So we have confidence level. Let's do a confidence level C is equal to 0.98. Come on. Okay. Stupid Apple, they did like these new ultra rounded rectangles in this new release of OS X. It's so annoyingly ugly. Sorry. My rants on the Apple forum. All right, so n is equal to 6 trials, right? And then my sample standard deviation is 1.14, so that's not S squared, that's just S. And my X bar is equal to, what is it? 532. Okay, so but no, use this mean to estimate the actual melting point, and what can the chemist assert with 98% confidence about the maximum error? So we're going to do both. We're going to do the error and the mean estimate. So X bar is 532.26, 532.26. I'm going to copy this guy here, put it down here. All right, and if I print it, I get that, oh, I didn't put the mean value correctly. The mean value is x bar. Hold on, did I get things correctly? So its estimate, do I have a mistake in the alpha s over square root of n? I think I have a mistake over there. Which one do I trust, the other one or this one? So 1.14. So let me run it with my other approach here. Do a better job, see what mistake I made. So I'm going to put 0.98 over here. N is equal to 6. And then my S is 1.14. 1.14. I got everything right. Yep, so I have a mistake on the slides. So the error margin is 1.6 degrees, about 1.6 degrees. And the melting point with 98% confidence, if I put X bar over here, is going to be between 531 and 534 degrees C. Yeah, there's a typo over there. Got to fix that. OK. Slides are wrong. All right, let's see. Another example. Should we spend some time on making a script that just does that for us? Does all of these problems for us so that you can use it on your exam, right? Should we do that? Let's just do that. OK. Let's just do that. Let's do a bulletproof script. How about, so we're going to do a script for both, should we call it compute confidence intervals? Compute confidence interval. And I want the script to also do, let's see, to do both the z-test and the t-test, OK? And we'll just give it a standard deviation. And then in one case, we treat it as true population standard deviation. In the other case, we treat it as a sample standard deviation. And you pick the statistic that, the test that matters to you. All right. You guys in the back can see? OK, def compute conf interval. Blah, we added documentation and stuff. And so we do a confidence level, conf level, and then a standard deviation, and then a sample size. And we're going to need a sample mean. But I'm going to default to a sample mean of 0. I tell you why. Because in case you are asked a question where you're only computing the error, so you call this function without passing on the sample mean, but internally, just like we did, we're going to use a sample mean of 0 in that case. If you pass a sample mean, we'll compute the sample mean that we want. OK. So the first thing I want to do is compute this. So let me go back here. So I want to compute these. OK, that's what I'm after. And now sigma over square root of n, or s over square root of n, I'm going to call that standard error. And that's going to be my standard deviation all over mp dot square root of sample size. Okay. So now I'm going to use this function to do both the z-test and the t-test. You just pass on whatever standard deviation you have. Okay? If you have a population standard deviation, then you pick the result from the z-test. If you have a sample standard deviation, you pick the result from the t-test. OK? Easy. All right, so we compute that standard error. And then first we'll do, let's do z-test first. So we do confidence interval low, and then CI confidence interval high, like we did last time. And that's stat.norm.interval. And confidence is equal to, if you look at stats.norm.interval, remember we have passed the confidence, or if you look up here, way up here, Where is it? Yep, confidence, location, scale, etc. Okay. So this is going to be the confidence level, and then the next one was the location, and that will be the sample mean. All right. If it's 0, it's just going to give us the errors, right? If not, it's going to give us the confidence interval. And then for scale, we want standard deviation over square root of n, but I already computed that, and I called that the standard error. So I got that. But then I also want to report the critical values, the z alpha over 2. Now, we cannot trick stats.norm.interval to give us the z alpha over 2, and so we might as well just compute them the way we did the way we did usually. So critical z values. So if you go back way up, I'm going to go real fast. You remember here we did alpha and then z minus, and that was the ppf alpha over 2, etc. Right? So let's do that over here. And actually, I'm going to define alpha over here is equal 1 minus conf level, critical z values. So we can get the z minus if you want, or z minus or z low, and that's stats.norm.ppf. Okay, and we give it alpha over 2, so that's going to give us a negative value, the z minus value, all right, alpha over 2. And then z plus is minus z minus. Agreed? Okay. So that's the z high value. And then the margin of error E is the upper bound on the interval minus the sample mean. If the sample mean is 0, then we already have that answer. If the sample mean is not, then that difference, because C high is equal, that's the upper bound of the confidence interval, it's equal to the sample mean plus the error. So the error is the upper bound minus the sample mean. All right? And that's it. So let's print some results. Print z test results. All right. So let's see how we did it. I'm going to copy some stuff from the previous script. So first of all, if the sample mean is not 0, then I'm going to print it. Sample mean, just to report on what we had. So sample mean, just copy what I'm doing here. Formatting is weird, but it works. Just copy it and then print standard error. So that's s over square root of n. Okay, s or sigma over square root of n. And that will be standard error. Standard error. And also let's put 3 figures here. Close this. And then also let's print which confidence interval we're doing. Confidence level, or confidence level, to confirm what confidence level we have. Confidence level, and we're going to do, this is the conf level times 100. So that's the percentage. Conf level times 100, and we'll just do one significant figure, and I'm going to put a percentage here. Okay, and I need to close this before that. Okay, so these are not related to the z-stats, honestly, so I'm just going to put them up here. Now we print the z results. Print z test Okay, this applies only, you pick up the z-test results when you know that the when you know the population standard deviation, and then print margin. We're going to print the margin of error, margin of. The reason I'm doing this weird formatting with print, because I want to control the number of significant figures. I don't want 16 digits after the decimal point. That's useless. So you have to format it in this kind of annoying syntax, but it works. Margin of error, that's going to be E, and we'll put also 3 figures here. Close it, and let's do print for the critical z-score. Critical z value. So that's the z alpha over 2. This will be, can put z plus if you want, or z minus. It's minus z minus. So, but I want a positive value. And we close parentheses. Let's see. All right, much better. What else do we have? The confidence interval. Print. F confidence interval. So remember how we can put the confidence interval, we can put it in parentheses, and then we close, and then I'm going to put here CI low and format it with 3 figures, and then CI high, and then 0.3 G. Okay, I think this is it. All right, let's try it. Let's try it out. Error. Blah, blah, blah. Oh, semicolon. Just colon. Okay. Let me try it out on this whatever this problem. Let's try this problem. Okay, so this problem gave us 39 and 44. Let's try it down here. I'm gonna run this, and then I'm gonna say compute conf interval, and then my confidence level is C, my standard deviation is sigma, that's a population standard deviation, my sample size is N, and then my sample mean is X bar. Ah, look at that, very nice. So it told me, it reported back to me, I'm computing with a sample mean of 42, my standard error was 1.1, so that's sigma over square root of 2 of n, and confidence level is 95% confidence, and it gave me margin of error 2.15, great, critical z value 1.96, so perfect, and then 39.8 and 44.2, which I believe were the results we obtained way above here. Yep, 39.8 and 44.2, right? Pretty neat. Okay, now it should take a second to do it for, yes? Oh, I don't know. I will try to make your wish come true, but how about this? It worked. Okay. Sorry about that. Yes? I thought you were going to ask me to turn this light on. Yes. Here? Okay, take a minute, because next, if you're already done with this, duplicate this, but do it for the t distribution, please. Okay? So we will output results both for z and t test, and you'll pick the one that is relevant to your problem. The key here is how you treat your standard deviation. Is it a population standard deviation or a sample standard deviation? Copy this block, paste it below it inside that routine, and change, make it work for a t distribution. Mm-hmm.
What did you write at the very bottom on the next cell?
Oh, so that's the problem at the top. If you scroll, if you still have your Jupyter notebook, I'm trying to make sure. Hold on. Okay, there you go. Yeah. All right, so now work this for the t-test, please. And I will float around like a feather. That's some real privacy screen. Like I can't see anything from here. That's cool. Do you need a charger? I think I have an extra one if you want. That's you. Do you have a cable? Hold on, I might just have the power supply. Oh, I do have power supply and cable. Perfect. Hold on. Do you have the mag? Would this work? It's USB-C. So do you have a cable? Yeah, sorry. Ah. Thank you. Okay, you guys doing it for T?
Yeah.
Okay, let's T. Coding error?
Yeah, I just mistyped it.
Oh.
Tells you exactly what the code is above, so I have to just retype perfectly. Is there like a setting somewhere?
To tell you what the code above? What do you mean?
So like we defined it as like sample size.
Oh.
And if I wanted to write sample size, I can't just copy and paste like you do.
Autocomplete, you mean?
Yeah, I can probably figure that out later.
Tab. You just press tab as you start typing. So start typing. Say sample or press tab. Nope. It doesn't. It's not turning on. Okay.
Yeah, I'll figure it out later. But
I don't know if it should automatically turn on. That's yeah. Is this Anaconda distribution?
yeah, Anaconda. There's probably a setting somewhere I can turn it on, but so far I don't do it.
Okay. So who's got the T distribution done? Okay. So now run the same. So rerun the same problem. It should output 2 results. And try to repeat the problem we did. Oh, you don't got. No. Can you run the notebook on here? Yeah. Okay, so that will be a nice problem for you to solve at home for your exam. Okay? So you make that test, add the t-test to that function, and it's literally just copy paste, change norm to t, and z minus to t minus, and you're done. Pardon me? All right. Let's continue with the slides. Actually, I'm going to need that script for subsequent problems. Oh, what the heck? I'll just do it. Okay, so what I'm going to do, I'm going to self-plagiarize. I'm going to copy and paste. Now we're going to do a t-test, stats.t, stats.t, t minus, t plus, t minus, standard error. I don't need this anymore because I already printed this. Okay, margin of error. And I'm going to call this here t-test. And this is t-value. Am I good? Yep. And then I get a parse argument. Hold on, what's going on here? Stats.t.ppf. Hold on. It's coming from here. Location, confidence level, location, sample mean, scale, standard error, and then t minus. Compute. Oh, yes, we're missing degrees of freedom. My bad. So we need degrees of freedom with the t-test. Okay, we need degrees of freedom with the t-test, and if you come back here, look at this, we need df over here. We forgot to put df. Okay, and then df is equal n minus 1. And sample size, that's correct. Thank you, Sam. Sample size. Good grief. Missing one argument. So it should go confidence level, df sample size minus 1, location sample mean, and then confidence. I don't think it's called, yep, it's called confidence, df, location, and scale, stats.t.interval, see the error. Oh, same thing for the ppf here. I need the df is equal sample size minus 1. All right, now it's working. So you pick the statistic that is relevant to your problem, okay? Sometimes the intervals, like in this case, they're pretty close to each other because the difference is probably in the higher significant figures. But then you can see, and as the sample size grows larger, the t-distribution becomes a normal distribution. Remember that. So your confidence intervals are going to start getting more and more identical. But notice the z value here, the z alpha over 2 is 1.96. This one is 2.03. So very, very close to each other. And the confidence intervals were identical in this case. But the margin of error here is a little wider than this one because you're using a sample standard deviation here. So you pick the test that matters to you. Okay, this confidence interval is not going to tell you, oh, you can only use the z-test or the t. You have to choose which test, which result you want to use. Okay? All right. So let's move on. Gotta move on. As another example, you can do that. Okay. Well, I wanted to touch on an interesting question here. I'm inclined to put this as a homework assignment because it's a fun little problem. It shows me kind of the depth of what you've been learning so far in our curriculum. So we remember with the normal distribution with the z-test, we were able to determine a minimum sample size to achieve a certain confidence level. Remember that? No? Okay, I can dig it out in the slides for you. Where is it? Minimum sample size, right? So remember this when we did this with the z-test. And then we made this argument about the discussion, and we determined we were able to extract n from the error margin, which was z alpha over 2 sigma square root of n. We were able to extract n given a certain confidence level or error margin or combination you want. So you have sigma fixed, and then you say, I want a confidence level of 90%. So that tells you alpha is 10%. And then you can estimate within a certain error margin, and you can estimate what your n needs to be, what your sample size needs to be. So before you go out and do a sampling campaign, you can estimate your minimum sample size to achieve the confidence level that you desire. All right. So we were able to do that calculation with the z-test. All right. Can we do it with the t-test now? So we run the same math. Let's run the same math. Okay. Our error margin is t alpha over 2 s over square root of n. All right. So we should be able to say that n is equal to t alpha over 2 s over e squared, right? That's the minimum sample size. All right. Okay, so we can I give an example here. And I say, okay, let's go back to these dental researchers. Now they want to find the sample size that would achieve an error of 3 nanometers and a confidence level of 90%. All right. Assume that the standard deviation is estimated as s equal 15.5 nanometers. All right, so go ahead and try to solve this problem. Open up your Jupyter notebooks or do the math. So you want to find the t-value with a certain confidence level. In other words, you know alpha over 2, that's the area to the left. So you can obtain the t value from the stats.t.ppf. And you have S and you have E. You should be able to compute N, correct? Look, I know you're kind of a little bit, you forgot what we were doing, etc., but I hope you start remembering things, at least after this lecture. This is an important question to see if you're really kind of catching up what we're doing. So go back to the Jupyter Notebook. The t value is an inverse lookup. You know that. And what is alpha? Well, alpha is 10% because my confidence level is 90%. So can you get me a value for n?
Are we supposed to plug and chug?
Yes. Why?
Because we need it to get the t.
Was that your answer too?
Yeah.
Okay. So can one of you explain it, or all together explain it to the rest of the class? You get a lot of chances to explain. How about you explain it?
T
Just-
is dependent on n.
Okay. So what your colleague is saying, we're trying to compute n, but t, the value of t depends on n. Stats.t.ppf, you give it the area to the left, comma, df, degrees of freedom, which is n minus 1. But you're trying to find n, but you need n to get t. What kind of equation is this? Okay, it's a nonlinear equation. What's your unknown here? N. N is your unknown, right? You're trying to find n, right? So do you remember your nonlinear equations from numerical methods? And also remember to stress out the fact that at one point I said sometimes we use this nomenclature for t to enforce the idea that t is a function of alpha and n as well. So you now have this implicit dependence, and t is not a linear relation in n. If t was n plus 1, you could solve this analytically. Okay? Even if t was, n squared, maybe we can find the root there. But t is a complex function as exponentials. It's very nonlinear. This is classic nonlinear equation. What do we do when we have a nonlinear equation? You write it in, what did you say? Residual form, correct. So that's for you to think about for your homework. And you'll see, in some cases, solving the nonlinear equation to find n is going to give you a much cleaner estimate for your minimum sample size. Okay, what would you put as an initial guess for your nonlinear solver? What would be a close estimate that we have an answer for? No, so the mean has nothing to do with the sample size, but
Could you find your z value assuming it was a
yes, so get the n value from the z-test and put that as your initial guess to get the n value for the t-test. They're going to be pretty darn close. And as n gets larger, they're going to coincide. But for small n, if you get it from the z value, so put your initial guess, n equals z alpha over 2 s over e. Gets you very close, and then you do a root, or I don't know, what did you do, f-solve or root in numerical methods? Do you remember? F-solve, yeah, so you can use it with f-solve, give it the residual function. Okay, great homework problem. Okay, next, we're done with means. Next, we want to do population variance. The next discussion we'll have is about population variances. So the same way we did confidence intervals on population means, we will do them for population variances. Standard deviation is derived from the population variance. We just take the square root of 2. So guess what's a point estimator for the population variance? It's the sample variance, right? The same way that the sample mean was a point estimate for the population mean, the sample variance is a point estimate for the population variance. There's no mystery there. Same thing for the standard deviation. S, or square root of S squared, is an unbiased estimator for the population standard deviation. Okay. Obviously, we're looking for interval estimates. And remember, this is what we had for sample means, and that allowed us to invert these formulas, the z value and the t value, to from them extract an error margin, because x bar minus mu is an error, correct? It's a form of error. But when you look at the sampling distribution of sample variances, and we said we're assuming the population is normal, and even if it's not, we will assume that they all follow a chi-squared distribution. So the equivalent of the t and z value for variances is a chi-squared variable, but that ends up being defined as n minus 1 s squared over sigma squared. There's no s squared minus sigma squared. Okay, so notice when we went to standard deviation and variances, there's no more of that error x bar minus mu, which we defined as the error. Over here, we don't have that. We have a ratio of s to sigma instead of s minus sigma. And it turns out that the variance, the type, it's a type of statistic where comparisons on the variance and moving forward, on the variance, we only do comparisons as a ratio rather than a difference. Unique property about the variances. So you don't compare the difference in variances in population 1 and population 2. That's a meaningless measure because that variance is a measure of scale of the population rather than a point, like the mean value is the central point. When you're measuring scales, how much larger is the Golden Gate Bridge compared to the Sandy Bridge, right? You take their ratio, right? So like 10 times bigger, 10 times longer, right? Same thing with the standard deviation, with the variance. It's a measure of scale of the distribution, how wide it is. And so it makes sense to take a ratio. And the math shows you that, but intuitively, that's understandable. All right. So, okay, we know that this combination of variables, n minus 1 s squared over sigma squared, together they make what's called a chi-squared distribution. We understand that distribution very well, and we can plot it. It looks something like this. My objective now is to, from this formula, somehow extract a confidence interval on the true population, sigma. Like, what can I say about sigma, given that I know s squared, or s. Okay. Now, we're going to do the same approach we did with the normal distribution and with the t distribution. We're going to draw an area in the middle, color it in pink, and call that C, our confidence interval. We have two areas on the left and the right in the tails. The difference between this distribution and the other ones is that this one is not symmetric. Okay? That's a key thing you have to keep in mind when you're calculating the critical values for the chi-squared distribution. So again, we're going to call this area shaded in pink C. That's it's going to be our confidence level. And we will call those two values here. So this chi-squared distribution. So on the x-axis, it's a chi-squared variable. I'll call this x chi-a squared and chi-b squared, or chi-low, chi-high. There's no chi-minus and chi-plus. Okay, this is chi-low, chi-high, or chi-a and chi-b, chi-squared b. Okay. And the area in the blue, same as we did before, the area in the blue is alpha. All right. Now, just given this, we know that the statement, this translates into the following mathematical statement, that the probability that chi-squared is between chi-a squared and between chi-squared a and chi-squared b is equal to c. That's what this translates to. Now, what is chi-squared? It's n minus 1 times s squared over sigma squared. We're going to do the same procedure to try to invert that formula. Now, if you take the inverse of this, you're going to have to swap the unequal signs, all right? Or take the inverse of that. So what you get is the probability that sigma squared over n minus 1 s squared is between, now notice now chi squared b is on the lower bound, because chi squared b is larger than chi squared a. So 1 over chi squared b is smaller. So it's going to go to the lower bound of the interval. And 1 over chi squared a is on the upper bound. And c is our confidence level. We haven't determined chi a and chi b, chi squared a and chi squared b yet, but those can be determined just from inverse lookup, like we did with the z and t values. Right? So what I'm after is finding a bound on sigma squared, and then you multiply by n minus 1 times s squared, which is a positive quantity, so it's not going to change the unequal signs here. And we get our confidence interval for sigma squared. So given a confidence level of c, then we can bound an s squared and a sample of size n. We can estimate the population standard deviation to be between those two values with confidence equal to c. But there's a problem. How do we choose chi squared a and chi squared b? Yes?
There's probably a CDF that we could do for chi squared a.
No, yes, so we can do an inverse lookup, so we can reverse it, but how do you choose them here? So if you remember in the normal and t-distribution, I said you can arbitrarily choose them as long as the area in the tails is alpha and the area in between is c. Then we said because the distribution is symmetric, we're going to choose them so that the areas in the tails are equal, so that they're in the middle. But over here, this is an asymmetric distribution, right? So chi squared a is not equal to minus chi squared b. They're not mirror images or anything like that. And in fact, they can be chosen randomly. I can move this however I want and maintain that area in the middle to be c and the area in the tails to be alpha. Yes?
Is the area under chi squared a the same as the area under chi squared b?
So above a chi squared b. So that's one choice that we can make, and it is the choice we will make. So what your colleague is saying, well, yeah, there's an infinite number of ways we can choose chi squared a and chi squared b. But the one, in advanced statistics we say that minimizes our lack of knowledge, is to choose in an unbiased way, is to choose chi squared a and chi squared b such that the areas in the tails are equal. Okay, so alpha over 2 and alpha over 2. But there's no symmetry here at all, so be very careful as you use this distribution. Unlike t and z distributions, which were symmetric, areas in the tail were equal, but also the z values were mirror images of each other. Chi-squared values are not mirror images. Okay? All right, so in fact, as long as the area in blue is equal to alpha, and a reasonable choice is to choose chi-squared a and chi-squared b such that the areas in blue are equal. So in other words, alpha over 2 here and alpha over 2 over here. Okay, so now don't hate me for what's going to come next. I didn't make this up. I'll tell you the person who made up this incredibly annoying nomenclature. So we're going to call chi-squared a as chi-squared 1 minus alpha over 2, although this is the value that corresponds to chi-squared such that the area to the left is alpha over 2. Okay, so it should be called chi-squared alpha over 2, right? I like to just call it chi-squared low, period. That's the one that has the smaller value of the two. Okay, the other one, they call it chi-squared alpha over 2. It should be called chi-squared 1 minus alpha over 2 because the area to the left of this guy is 1 minus alpha over 2, or the area to the right is alpha over 2. So I don't know why they chose this nomenclature. It's annoying. It's non-descriptive, but it contradicts everything we said about our nomenclature earlier. But as long as you remember that the area to the left of this value is alpha over 2, the area to the right of this value is alpha over 2, whatever you call it, as long as you keep track of that, you're okay. I like to call them chi-squared low, chi-squared high. It's unambiguous. One of them is the smaller value, area to the left is alpha over 2. One of them is the larger value, area to the right is alpha over 2. Okay, don't get entangled in the nomenclature, right? But you should know that that's the nomenclature that is used. Okay? In fact, what they did, they flipped all the nomenclature we used so far, and they designate by the subscript the area to the left, to the right, instead of the area to the left. Anyway, don't take me for this. All right. So then, once we recognize this, then we can substitute these values, because these values, we obtain them, you know C, therefore you know alpha, therefore you can obtain these chi-squared low and chi-squared high from the PPF of the chi-squared distribution, all right? And then you can plug them in, and there you go. You have your confidence interval, and you can just simply write it this way or put it in parentheses. It's a confidence level, it's a confidence interval on the population variance, okay? If you want it on the standard deviation, you simply take the square root of that, all right? And here I described to you that for this value, you do a reverse chi-square lookup with area to the left, alpha over 2, and this is reverse chi-squared lookup with area to the left, 1 minus alpha over 2. Be careful. You have to compute those independently. You can't do chi-squared high is equal minus chi-squared low. That's wrong. Okay, these are not symmetric values, and this is not a negative variable. So both values are going to be positive. Okay, and if you find this nomenclature confusing, like I do, okay, you gotta blame this guy, Carl Pearson. He's a big name in statistics. In fact, like Pearson Education, Pearson Press, like the guy that's after him. Look at him. I'm gonna turn off the lights a little bit. He's like looking at the future. I'm gonna mess up every generation with this confusing nomenclature that I invented. And look at him standing here, looking out the window for a portrait. This one, he's very conspiratorial, and this one is like sitting with this person, like, you know, planning for the demise of statistics. And like, look at that. It's like the Mona Lisa. Anywhere you look, he's looking at you, right? Anyway, okay, so he's the guy behind that nomenclature, not me. I call them chi-squared low, chi-squared high, and I'm happy with that. All right, so this is a pseudocode or algorithm of what you need to do. Find the point estimate based on the level of confidence, calculate alpha over 2 and 1 minus alpha over 2, and use the chi-squared distribution to find the critical value. So the PPF in Python, or a reverse lookup if you're using Sheets or something else, and then do the calculation. Now what's cool is that thankfully we also have the chi-square distribution in Python, and it does have an interval routine, so we get the interval automatically without having to get confused about chi-squared, et cetera, et cetera. However, the way that this is set up is it's not going to give you the confidence interval. It's going to give you the chi-squared value, the low and the high values. So notice here how I write lower chi-squared and upper chi-squared. That's what the interval does. So although it's called interval, again, don't blame me for this. Blame SciPy people for why they designed it this way. The interval function for chi-squared is not going to return a confidence interval. It's going to return the critical chi-squared values. You need to take those values and multiply them by n minus 1, whatever that formula we had here, this formula, right? So you got to take this is chi-squared high, and this is chi-squared low, and you need to multiply n minus 1 s squared divided by this to build your interval. So there's one more step in the calculation that we need to do. Okay, let's do an example. A seed company is researching the consistency in the output of a new hybrid tomato plant that was recently developed. Okay? The weights of a random sample of 75 tomatoes produced by the hybrid plant are measured in pounds, and the sample has a variance of 0.0225 pounds squared. Right? Construct a 90% confidence interval for the variance in weights for all tomatoes produced by this new hybrid plant. So we will use Python to just do this in one shot. Well, in a few shots. All right. Now we're going to do this hybrid tomato plant. Okay. All right. And what do we have here? We have n is equal to 75. N is equal to 75 sample size. And then we have our confidence level is 0.9. So alpha, before I compute alpha. And then my variance is 0.225. So S2, S squared, 0.225. This is pounds squared, okay? All right. So that's conf level. First thing I want to compute is alpha. Actually, I don't need to do that. I can just, I'm going to call this guy over here, okay? Confidence and df, that's all I need for this. Right, remember the chi-square distribution requires the degrees of freedom like the t distribution. Okay, so where does this df come from? It's because the chi-square distribution ends up being a ratio of two distributions, normal and, okay. All right, so chi or low, chi squared, and then high. That's the order that stats dot chi2 dot interval does it. Okay, confidence interval with equal areas about, again, this documentation is nonsense, it's wrong. Just give it a confidence level, confidence equals C, and then df is equal to n minus 1. So if I run this and then print low chi squared and then high chi squared, I'm going to get 55.2 and 95.08. Let me see if I got this right here. Okay, there you go. So if I did this by hand, I got the same answer for the low chi and the high chi. Okay, they're always going to be in that order. And if you're like confused, if you put chi A or A and B, and is the lower value is going to be the lower chi squared, and the higher value is going to be the higher chi squared. And then your confidence interval is going to be this guy. So for the confidence interval, we still need to do one more step, Ci low. It will be n minus 1 times s squared over what? High chi squared, right? Because that's going to give us the smaller value. And Ci high is also n minus 1 times s squared over low chi squared. And then print Ci low, and then Ci high. And indeed, that gave me an estimate on the variance in the population, that my true population variance is between 0.02 and 0.03 pounds squared. Okay, that's the variance I have in my true population. You can take the square root of those. So print mp dot square root of Ci low to get the standard deviation in pounds. Ci high. All right, so the standard deviation, or the scale in the population, is 0.13 to 0.17 pounds. That's the standard deviation estimate for the population. Okay, just going from the sample standard deviation or the sample variance. All right, so that's the only kink in this problem is with chi-squared, is recognizing that you have low and high values, and then you have to build the intervals yourself. Okay, that's the only difference compared to what we did earlier with the z values and the t values. Okay? And we can embed this in our confidence interval estimate. So we can do everything in one go. We can do a z-test, a t-test, and a chi-squared test. The chi-squared test is going to be on the standard deviation, but the z and t tests are going to be on the mean value. Okay, there's only one test you'll do on the standard deviation. You assume you don't know the if you know the population standard deviation, you don't need the chi-squared test, all right? But in on all other cases, you don't. So we can embed this in our, in fact, I'm just going to copy and paste this up here. We can embed this here. So we do everything in one shot. Let's do a chi-squared test. And I'm going to print this, CI low, CI high. All right. And I got here, I got what? Conf level. And DF is sample size -1. And I'm going to paste this here, chi-squared test. There's no margin of error because there's no sigma plus and minus, right? There's no error margin. It's just the margin between, for sigma, it's between this and that value. There's no central point there. It doesn't mean, oh, sigma is in the middle plus or minus. No, it doesn't work that way because sigma is a scale measure. It's not it's not like the mean where you center it and you go above and below it. Sigma is a scale measure. It comes from a ratio. And you'll see that becoming more relevant when on the next chapter when we compare two populations to each other. So I'm going to eliminate this one, and then I'm going to do chi-squared low. I'm going to put this one low, chi2, and this one chi-squared high, and this will be high, chi-squared. And the confidence interval is going to be CI low and CI high, which is great. Yep. So now I can run this test. I can run this again on all of these tests. Look, it gave me a chi-squared test here, although that's not the question I'm asking for this problem. Yeah, so I don't have to pick the answer over here. Okay, neither for this problem, but for this one, okay, compute confidence interval. And what I will do is conf level is equal to C, and then standard deviation is equal to square root of S squared, right? Because we're giving the standard deviation. And then sample size is equal to N. And I can just run that and be the square root of T. Okay. And then it gave me, hold on. It gave me these values, right? So 0.0175 and 0.0302. And it gave me the chi-low and the chi-squared low and chi-squared high. Yes?
So this isn't giving you a rough estimate of your population variance. It's telling you the scale, just the scale.
It is giving you no, I'm saying the population variance is a scale measure. That's why we don't have a plus or minus. It's a ratio. So the variance, the standard deviation is a measure of is scale. Its square is also a measure of the scale. But what I'm saying is that the reason there's no error margin plus or minus because it's a scale measure. You're comparing ratios. You're not comparing differences. Like how larger is the bridge, the Golden Gate Bridge compared to whatever, some other bridge, right? You take their ratio, not the difference between them. So that's why you don't have a plus or minus.
So is this interval the ratio between the sample?
No. The reason that you end up with so there is no central point here. Sigma squared is between these two values, but I can't tell you what the error bar is, what the error margin is. It's undefined here. There's no definition of the error margin, like we did for the mean value. The mean value, we said, the true population mean is between sample mean plus or minus error. Here, we're not saying the population standard deviation is within sample standard deviation plus or minus an error. That's ill-defined. Because in the end, the comparison between the sample standard deviation and the population standard deviation is S over sigma, not S minus sigma. So that's why you don't have that. That's the only comment I'm making here, right? So I can't ask you, oh, what is the error margin for sigma squared? It's an undefined question. We're not talking about error margins here. because the comparison starts from the ratio of S over sigma, not S minus sigma. So one way you could, if you want, work out the math to say it is that, oh, my population standard deviation is about 1.2 of my sample standard deviation, rather than sample standard deviation plus something. Okay?
Okay, that was what I was.
Yeah.
So it's just
This is not the, but yeah, it's not a factor. This is not, again, this is directly on sigma squared. Okay? S, if you want to put sigma squared over S, you can extract that from the math, and then you'll get n minus 1. So if you want, what you're looking for specifically, it's not commonly reported that way, but you know what you can do here is say, okay, I'm just going to divide by S squared, so I measure sigma squared over S squared is between this and that. But again, that's not a margin of error, it's a factor, right? It's 2x your sample variance, or 3 times your sample variance, or 0.5 of your sample variance. Okay. Yes?
I'm not sure how to explain this. Can you go over again why CI low and chi high?
Yeah, sure, absolutely. Okay, so just basic math. This is smaller than this one, agreed? So let's say this is 5 and this is 10, just for the argument. When you invert that, 1 over 5 and 1 over 10, which is larger, which is smaller? 1 over 10 is going to be smaller than 1 over 5. You got it? Yeah, so when we divide, so when we took this formula here and inverted it, okay, hold on. Okay, there you go. First step we had sigma at the bottom, sigma squared at the bottom, and S squared at the numerator, and chi low and chi high. When we took the inverse, okay, they're going to swap. Or you take the inverse and you invert the signs, or you can rearrange them to keep the signs the same order, okay? So the inverse of an inequality, you have to swap the inequality. Yes?
In the code that you did, S2 for the code is the standard deviation, or is it the square of the standard deviation?
What do you think?
I think it's the standard deviation. Okay, it's a square.
It's the variance. That's why I called it S2. Okay, let me see. I'm going to have a couple of slides, and I know you're ready to go. Okay, so there's another example here. We can cover this in the first few minutes of the next lecture. And then what I have left is us doing this with proportions. We can spend a few minutes on Thursday on this, and then we'll take this to the next level. We're going to start comparing different populations, okay, which will set us up for hypothesis testing. So what we will do next time, did my radon, well, we're not going to ask that question yet, but we're going to compare my radon mitigation before and after, okay? We're going to get a ton of data, and we're going to see how we're going to compare that and see what it tells us, okay? All right, Godspeed, see you on Thursday.